In Rome, 1570, the air in the Vatican's kitchens was a wall of heat and noise. This was not a kitchen for a family. It was a food factory for the papacy, a place of organized chaos. Hundreds of cooks, scullions, and servants moved with a purpose that looked like panic to an outsider. At the center of one section near the roaring fires was Bartolomeo Scappi. He was not just a cook, he was the Cuoco Segreto, the private chef to Pope Pius V. His word was law here. Today, a great banquet was planned. One of the many courses involved fritto misto, a delicate mix of fried vegetables and small fish. Dozens of huge bronze pans filled with expensive olive oil sat over specially designed charcoal stoves. The temperature of that oil was everything. Too cold, and the food would be a greasy sponge. Too hot, and it would scorch to a bitter char in seconds. Scappi had no thermometer. Such a device for cooking was centuries away. He had something else, he had experience, and he had a tool. A young apprentice, sweating and nervous, stood by a pan. He looked at Scappi, waiting for the signal. Scappi held up a hand. He took a long, slender tool from a hook on the wall. It was a spicchiola. It looked simple. A small, perforated metal bowl, almost like a flat spoon full of holes, attached to a very long iron handle, maybe 4 feet long. The handle was the most important part. It was a tool for distance. It was a tool for safety. Scappi deftly scooped a single tiny piece of batter-coated artichoke from a bowl. He extended the spicchiola, his body a safe distance from the shimmering, dangerous oil. He gently lowered the metal bowl into the pan. He did not watch the artichoke. He watched the oil. He watched the way the bubbles formed around the batter. Were they slow and lazy, or were they frantic and furious? He listened. Was the sound a gentle sizzle or an angry hiss? This was his thermometer. The reaction of the oil on this one sacrificial piece told him everything. After a few seconds, he was satisfied. The bubbles were sharp and lively, but not explosive. The sound was a confident, steady fry. He lifted the spicchiola out, the golden brown test piece draining instantly through the holes. He nodded at the apprentice. Now, the apprentices, using similar long-handled tools, began to carefully lower baskets of food into the vats. Scappi's simple test, using a tool designed to keep the human hand far from a violent reaction, ensured the perfection of hundreds of dishes. That tool, the spicchiola, was born from a need. The need to test, to retrieve, and to drain, all while staying safe from the painful splash of 350-degree oil. And it was a specialized version of a spoon, adapted for a specific dangerous job. Today, you can buy its direct descendant in any kitchen store. We call it a spider strainer. It has a long handle. It has a wire mesh bowl. We use it to lift fried foods out of hot oil, draining them as we go. The technology is barely different. The metal might be stainless steel instead of iron or bronze, but the shape and the function are identical. It is a perfect, unbroken line from the papal kitchens of the 16th century to the pot of French fries on our stove today. It's a reminder that our modern problems in the kitchen are often very old problems with very old solutions, just dressed up in new materials. Number 10, your spice grinder is just a really fast rock. Hildegard of Bingen paused. It was the year 1158. Inside the infirmary of her new monastery at Rupertsberg, the afternoon light was thick with dust motes. She was surrounded by the scent of dried herbs, beeswax, and old parchment. Before her on the heavy oak table was a mortar and pestle. It was not a small, dainty thing for a bit of kitchen spice. It was a massive piece of carved soapstone, weighing at least 30 pounds, its interior worn smooth from decades of use. The pestle was a heavy, club-like stone, cool and solid in her hand. Her task was to prepare a remedy for a persistent cough that was troubling one of the sisters. Her own medical texts, the Physica, recommended a mixture of galangal root and cloves. These were not common ingredients. They were fantastically expensive, brought thousands of miles along dangerous trade routes. A single clove, to a common laborer, could represent a full day's wages. To waste them was unthinkable. She placed 3 small, dried pieces of galangal root and 5 desiccated cloves into the bowl of the mortar. First, the crushing. She raised the heavy pestle and brought it down with a solid, deliberate thump. Not a wild smash that would send precious fragments flying out, but a controlled, forceful press. Thump. 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 The tough, woody spices cracked, releasing their first sharp medicinal perfume. This was the brute force part of the job, breaking the structure. Then the grinding began. This was the part that required patience. She changed her grip on the pestle, holding it firmly and pressing down into the bowl, dragging it in a slow circular motion against the stone walls. The sound changed from a crack to a rough grating scrape. Scr, scr, scr. It was a physical process. She could feel the resistance of the spices through her arms and into her shoulders. It was a slow conversation with the ingredients. As she worked, the texture changed. The initial coarse grit slowly, minute by minute, gave way to a finer, more uniform powder. The aroma intensified, filling the small room. She could smell the heat of the galangal, the sweet punch of the clove. She would stop, use a small brush made of boar bristles to sweep the powder down from the sides of the mortar, and begin again. The entire process for this tiny amount, maybe a tablespoon of powder, took her nearly 15 minutes of continuous, focused effort. The final result was a fine, potent dust, ready to be mixed with honey or steeped in warm wine. This tool, the mortar and pestle, was fundamental to her work. It was her pharmacy, it was her spice rack, it was a machine powered by her own strength, a tool for transformation that was as old as civilization itself. For thousands of years, this was the only way to turn a hard seed, root, or crystal into a powder. Fast forward to last Tuesday. I was making a curry. The recipe called for freshly toasted and ground cumin and coriander seeds. I put a skillet on the stove, tossed in a tablespoon of each, and swirled them around for about 60 seconds until they smelled nutty. Then I tipped them into my electric spice grinder. It's a small, unimpressive plastic and metal appliance that costs about $20. I put, the lid on, a simple plastic cap with a built-in button. I pressed the button. The noise was instantaneous and violent. A high-pitched, furious whir filled my kitchen. Inside the small chamber, a tiny blunt metal blade was spinning at something like 20,000 revolutions per minute. It was not crushing, it was not grinding, it was pulverizing. The seeds were not being persuaded to give up their form. They were being shattered by immense localized speed and impact. The whole process took 7 seconds. I shook the grinder once, gave it another 3-second burst, and it was done. And I opened the lid. A puff of aromatic dust, far finer than Hildegard could have ever achieved, billowed out. The smell was intense, almost overwhelming, because every single cell of the spices had been violently ruptured in an instant. There was no slow release, no conversation. It was a sudden, total extraction of flavor. The technology seems worlds apart. Hildegard's heavy stone, my cheap plastic grinder, but the function is identical. Both are designed to do one thing: reduce a solid to a powder through the application of force. Her force was manual, slow, and deliberate, a process of crushing and abrasion. My force is electrical, fast, and brutal, a process of high-speed impact. My grinder is just a rock, but a rock that I can spin at the speed of a drill bit. We gained something incredible with this leap. Time, 15 minutes of hard labor for a tablespoon of spice is a luxury most of us cannot afford. 7 seconds is nothing. It allows us to access the flavor of fresh spices for a weeknight meal, something that was once reserved for the wealthy or the dedicated. But we lost something too. We lost the connection, the physical act of transformation. Hildegard felt the spices breaking down. She smelled the aroma build gradually. She controlled the texture with the pressure of her own hand. My process is a binary one. It's either whole seeds or dust. There is no in between. The machine is a black box. I put something in, I press a button, and I get something else out. The magic happens inside, hidden from me. Hildegard's magic happened in her own hands. Number 9, your rotisserie oven is a mechanical dog. The Great Hall of Haddon Hall in Derbyshire, England, was a scene of controlled bedlam in the winter of 1585. The Duke of Rutland was hosting a feast, and the centerpiece was to be a whole roasted pig. In the cavernous kitchen, the heat from the main fireplace was so intense you could feel it from 20 feet away. The fireplace itself was a huge stone cavern, big enough for a man to stand in, with a fire of massive logs roaring within. In front of this inferno, the pig was slowly turning on a heavy iron spit, and turning the spit was a dog. It was not a pet. It was a purpose-bred machine made of flesh and bone. He was a turnspit dog, or a Canis vertigus, the dizzying dog. He was a long-bodied, short-legged, strange-looking creature bred for one miserable job. His name was Pip. He stood inside a large wooden wheel, maybe 3 feet in diameter, mounted high on the wall near the fireplace. The wheel was connected to the spit by a series of chains and pulleys. As Pip walked, the wheel turned. As the wheel turned, the chain pulled, and as the chain pulled, the pig roasted. Pip's world was heat, smoke, and endless walking. He walked on and on and on, his paws patting on the worn wooden slats of the wheel. He couldn't stop. If he slowed, a kitchen boy would toss a hot coal into the wheel near his feet to encourage him to speed up. The pig was large. It would take at least 4 hours to cook through. Pip would not walk for 4 straight hours. The household kept 2 turnspit dogs. After 2 hours of grueling, hot, monotonous work, a cook would open the wheel, let a panting and exhausted Pip out, and put his partner Meg in for her shift. This was high technology for the 16th century. A spit needed to turn constantly for even roasting. A human could do it, but that meant tying up a servant for hours, a servant who could be doing other tasks. The turnspit dog was an early form of automation. It was a self-propelled engine fueled by scraps from the kitchen that performed a single repetitive task. The system was ingenious, if cruel. It harnessed the biological motion of an animal and converted it into the mechanical motion needed for cooking. For hundreds of years, in the kitchens of wealthy homes, manors, and castles across Europe, the sight of a small dog trotting endlessly in a wheel was the sign of a serious meal being prepared. The breed is extinct now. Once the mechanical clockwork spit, the clock jack, was invented in the 18th century, the turnspit dog's purpose vanished, and so did the dog itself. Last Sunday, I decided to make a roast chicken. I went to the store, bought a 4-pound bird, and brought it home. I rubbed it with salt, pepper, and herbs. Then I opened my countertop rotisserie oven. It's a miracle of modern convenience, a glass and metal box that costs about $100. I took the spit from the oven, a simple steel rod with 2 forks. I pushed the rod through the chicken, secured it with the forks, and slotted it into the oven. I pressed a button for chicken and another to set the timer for 75 minutes. Inside the box, a small silent electric motor whirred to life. The spit began to turn, a slow, steady, perfect rotation of about 2 revolutions per minute. The electric heating elements, one at the top and one at the back, glowed a steady, controlled orange. There was no smoke, no roaring fire, no exhausted animal, just a quiet hum and the gentle, even application of radiant heat. I walked away. I read a book. I did some laundry. I completely forgot about the chicken until the oven beeped politely to let me know its work was done. I opened the door and was greeted by a perfectly cooked golden brown chicken, its skin crisp, its meat juicy. The entire process required about 3 minutes of my active participation. The other 75 minutes were handled by a machine that did its job flawlessly, quietly, and without complaint. My rotisserie oven is Pip, the turnspit dog. The principle is exactly the same. Rotate a piece of meat in front of a heat source for even cooking. The problem of how to achieve that constant rotation has just been solved differently. The 16th century solution was biological. It took a living creature with all its needs and miseries and forced it into a mechanical role. The 21st century solution is electrical. It takes the invisible abstract power from the wall socket and uses a simple motor to achieve the same end. We gained a staggering amount of convenience and, it must be said, a huge dose of humanity. We no longer have to breed a creature for a life of servitude in front of a fire. My kitchen is clean, cool, and quiet. My effort is minimal, but the connection is different. The cook in Haddon Hall was intimately aware of the roasting process. They had to manage the fire, watch the animal, check the speed of the rotation, and oversee the entire, very physical process. My interaction was with a button and a timer. The machine handled the rest. The result is the same, a delicious roasted bird. But the journey from raw to cooked has been transformed from a loud, hot, labor-intensive collaboration with a living creature to a silent, sterile, automated process. Number 8, your grain mill is a tame volcano. Her name was Ragna, and she lived in a longhouse on the Orkney Islands around the year 950. Every morning, before the sun was fully up, her first and most important task began. It was the task that sustained her family, making flour. She knelt on the hard-packed earthen floor in the smoky central room of the longhouse. In front of her was the cornstone. It was the family's engine. It turned hard, inedible grain into the stuff of life. The quern was made of two heavy, circular stones, about 18 inches across, quarried from the island's tough sandstone. The bottom stone, the bed stone, was stationary and slightly domed. The top stone, the runner stone, had a hole in the center and a smaller hole near the edge for a wooden handle. It was incredibly heavy. Lifting the runner stone on and off the bed stone was a two-person job. Ragna took a scoop of dried oats from a leather sack. This was grain her family had grown and harvested themselves in the short, windy summer. She poured a handful into the central hole of the runner stone. She gripped the wooden handle. Then she began to turn. It was back-breaking work. She had to push the heavy stone around and around while also pressing down to create the friction needed for grinding. The grating sound of stone on stone, interspersed with the crunching of the grain, was the first sound her children heard every morning. As she turned the stone, the oats were caught between the two rough surfaces. The stones didn't just crush the grain, they sheared it. The oats were slowly worked from the center of the quern to the outside edge, becoming finer and finer as they went. A coarse, gritty flour, what we might call meal, began to spill out from between the stones onto a stretched animal hide below. Her flour was not fine or white. It was rough, full of bran and grit from the stones themselves. This stone ground quality was not a rustic choice. It was an unavoidable reality that wore down the teeth of everyone who ate the bread. To make enough flour for one day's baking of flatbreads for her husband and 3 children, Ragna had to work the quern for at least an hour, sometimes 2. Her shoulders and back ached. It was a relentless daily grind that consumed a huge portion of her energy. The quernstone was a tool of survival, but it was a demanding master. For thousands of years, from the Neolithic period to the rise of the watermill, this was how the vast majority of humanity got its flour by hand with 2 stones. Last month, I got interested in baking with fresh milled flour. I bought an electric grain mill, Como Mio. It's a beautiful little thing. It's a compact box made of beechwood and a high-tech composite material. Inside it, hidden from view, are 2 grinding stones. They aren't sandstone. They are made of corundum, fused in a ceramic matrix, a material so hard it's used for industrial abrasives. To make flour, I took a cup of whole wheat berries and poured them into the hopper at the top. I turned a knob on the front to select the fineness of the grind, from coarse, cracked wheat to pastry fine flour. I flipped a switch. The machine came to life with a loud but not unpleasant roar. It is the sound of immense power in a small space. The 400-watt motor was spinning one of the corundum stones at high speed against its stationary partner. The wheat berries were fed from the hopper down into the grinding chamber. In a matter of seconds, they were utterly obliterated. The machine was not just grinding, it was shattering the grain with engineered precision. A warm, wonderfully fragrant, incredibly fine flour began to pour out of the chute into the bowl I'd placed below. The process of turning 1 cup of hard wheat berries into 2 cups of soft, fine flour took less than a minute. The motor didn't strain, the machine didn't labor, it just did its job with terrifying efficiency. My grain mill is Ragna's quernstone. Both use the same ancient principle, 2 stones, 1 stationary and 1 rotating to grind grain, but the source of power has changed everything. Ragna's power was her own body, a limited and precious resource. My power is the electrical grid, a vast, abstract, and seemingly limitless resource. Her quernstones were natural rock, which wore away into her food. My grinding stones are a feat of material science, designed to be almost indestructible. The gain is almost incalculable. A task that consumed hours of grueling labor and defined the daily rhythm of life for someone like Ragna is now a minor, 1-minute task for me. I can have the freshest possible flour with all its nutrients intact with the flip of a switch. It's a miracle of modern engineering. But what is lost is the visceral understanding of what bread is. Ragna knew, in her muscles and bones, the energy required to make a single loaf. For her, a piece of bread represented a real, tangible chunk of her life's labor. For me, it represents a minute of a machine's time. The flour just happens. The connection between the hard kernel of wheat and the soft loaf of bread is broken by the sheer, overwhelming speed and power of the machine. Number 7. Your George Foreman grill is a soldier's campfire tool. France, 1347. The Hundred Years' War was dragging on. John, an English longbowman, was huddled with his company around a small, smoky campfire. They were on the move constantly. There were no kitchens, no permanent hearths. Their cooking equipment had to be light, durable, and simple. Tucked in John's pack, next to his spare bowstring and a whetstone, was his gridiron. It was a simple, clever piece of blacksmithing. It was essentially a metal grate, about a foot square, made of wrought iron bars. It had short 3-inch legs on each corner and a long handle on one side. Some versions were even hinged to fold in half for easier packing. Its function was basic to hold food above the hot embers of a fire. It was a way to create a clean, flat cooking surface in the wild. Tonight they had a rabbit, acquired from a local snare line. After skinning and gutting the animal, they sectioned it. John took his gridiron and set it over the best part of the fire, the glowing red coals that gave off intense, even heat without the foul-tasting smoke of open flame. He placed a few pieces of the rabbit onto the hot bars. The sound was immediate, a sharp sizzle as the meat hit the metal. The fat began to render and drip down, kicking up little flares of flame and fragrant smoke. This was direct heat cooking in its most raw form. There was no temperature control knob. John controlled the heat by moving the gridiron closer to or farther from the embers, or by shifting the pieces of meat to hotter or cooler spots on the grate. After a few minutes, he used the tip of his knife to flip the pieces over. The side that had been down was now beautifully seared with dark lines from the iron bars. This was more than just cooking. It was a quick, efficient way to make tough, gamey meat palatable. The high heat seared the outside, and the open design allowed fat and juices to drip away. It was a tool for soldiers, for travelers, for anyone who needed to cook a meal quickly over an open flame without a proper kitchen. It was one of the most basic and widespread cooking tools of the medieval period, a simple piece of metal that turned a campfire into a stove. Now, consider my kitchen counter last night. I wanted a quick dinner. I took a chicken breast, flattened it slightly, and seasoned it. I pulled out my George Foreman grill. It's a plastic and non-stick metal contraption, a bivalve appliance that opens like a clamshell. I plugged it in. A small orange light came on. I waited about 3 minutes for the light to turn off, indicating it had reached its preset cooking temperature. I opened the lid and placed the chicken breast on the bottom grill plate. This plate, like the top one, has raised ridges. I closed the lid. The top plate made contact with the top of the chicken. The sizzle was immediate, just like John's rabbit. But something different was happening. My chicken was being cooked from both sides at once. The heat was coming from electric elements embedded inside the metal plates. Because the grill is sloped, fat and juices rendered out of the chicken, and instead of dripping into a fire, they ran down the channels between the ridges and into a small plastic tray I'd placed at the front. The cooking process was incredibly fast. In about 6 minutes, the chicken was cooked through. I lifted the lid. The chicken breast was perfectly cooked, and it was branded with the characteristic dark grill marks on both the top and the bottom. There was no smoke, no fire, no guesswork. My contact grill is John's gridiron. The core principle is identical cooking food quickly with direct, conductive heat transferred through hot metal bars. The grill marks we find so appealing are a direct aesthetic inheritance from the medieval gridiron. But the execution is a world away. John's gridiron cooked from one side over an unpredictable fire. My grill cooks from two sides with a perfectly controlled electric heat source. The evolution from the gridiron to the contact grill is a story of taming fire. John had to manage a real open flame. It was smoky, messy, and required skill. My grill has taken the fire and hidden it inside. The dangerous, unpredictable part of grilling has been engineered away. What's left is the result: quickly cooked meat with grill marks. We gained speed and incredible convenience. The ability to grill indoors on a Tuesday night with no mess is a modern marvel. But we lost the flavor of the smoke. We lost the connection to the fire. John's rabbit tasted of the animal, the iron, and the wood smoke from the forest. My chicken tastes of chicken and seasoning. The tool has been perfected to the point of sterility. It does its one job with ruthless efficiency, but the soul of the fire has been lost along the way. Number 6. Your slow cooker is a peasant's cauldron. Imagine a small one-room peasant cottage in 14th century England. The floor is packed earth. The walls are wattle and daub. The roof is thatch. In the center of the room is the most important feature of the house, the hearth. There is no stove, no oven. There is just a shallow pit where a fire is kept burning nearly all the time. This fire is for heat, for light, and for all cooking. Suspended over the fire from a chain or a tripod is a large, round-bellied, three-legged iron pot. This is the cauldron. For the woman of the house, perhaps named Eleanor, this cauldron is her entire kitchen. It is likely the most valuable single object her family owns, an item to be passed down through generations. In the morning, she adds water to the cauldron. As the day goes on, everything goes into the pot. A handful of oats, a few rough carrots and onions from their small garden plot, a bone from a previous meal to give flavor. If they are lucky, a small piece of salted pork or a foraged squirrel. The contents of the pot are never the same, but the process is. It is a perpetual stew, or pottage. The cauldron simmers away over the low fire for hours and hours. It is never emptied completely. Each night the family eats a ladleful of the thick, soupy mixture. The next morning more water and new ingredients are added to what remains. This method of cooking was born of necessity. The fuel, wood, or peat was precious. Keeping one fire going at a low level all day was far more efficient than building a hot fire for each meal. Tough, cheap cuts of meat and stringy root vegetables, inedible if cooked quickly, would become tender and digestible after simmering for 8 or 10 hours. The cauldron was a machine for extracting every last bit of nutrition and flavor from whatever scraps were available. It was the original one-pot meal, a slow, gentle, and fuel-efficient way to feed a family. Last weekend, I made pulled pork. But I had a 5-pound pork shoulder, a tough, fatty, and inexpensive cut of meat. I rubbed it with spices. Then I took out my crock pot, my slow cooker. It's an oval-shaped ceramic pot that sits inside a metal housing. It is not a complex piece of technology. The metal housing contains a simple, low-wattage, wraparound heating element. That's it. I placed the pork shoulder inside the ceramic pot, added a bit of liquid, and put the glass lid on top. I plugged it into the wall. I turned the dial to low. Then I left. I went to the store. I met a friend for lunch. I was gone for 8 hours. While I was away, that simple heating element was slowly, gently raising the temperature of the pot's contents to a steady simmer, just below boiling, around 200 degrees Fahrenheit. There was no fire, no smoke, no danger, just a tiny, steady trickle of electricity being converted into heat. When I came home and opened the front door, the house was filled with the rich smell of cooked pork. I lifted the lid of the slow cooker. The tough cut of meat had been completely transformed. It was so tender that it fell apart at the touch of a fork. The connective tissues and fats had rendered down, creating a succulent, flavorful meal from a cheap piece of meat. The entire time I was actively involved in this process was less than 5 minutes. My crock pot is Eleanor's cauldron. They perform the exact same function to cook food slowly over many hours using low, steady heat. Both are designed to make tough, cheap ingredients delicious and tender. Both are incredibly energy efficient. Eleanor conserved her precious firewood. I conserve electricity. The slow cooker uses about as much power as a standard light bulb. The technological leap is in the heat source and the control. Eleanor's cauldron was heated by a real living fire that had to be tended and managed. The temperature was inconsistent. The cooking was imprecise. My slow cooker is heated by a controlled, predictable electrical element. It maintains a perfect, steady temperature for as long as I tell it to. It is a safe, domesticated fire in a box. We gain safety and freedom. I can leave my house for 8 hours with my slow cooker on and have zero fear that it will burn down. The process is completely automated. I am not tied to the hearth, but the central role of the tool has vanished. Eleanor's cauldron was the heart of her home. The family gathered around it for warmth and food. It was a constant simmering presence in their lives. My crock pot is an appliance. I store it in a cabinet. I bring it out when I need it. It does its job in a corner of the kitchen, silently and without fanfare. It is an incredibly useful tool, but it is not the center of anything. It is just another box that makes our lives a little bit easier. Number 5. Your waffle iron is a rich man's coat of arms. In the city of Ghent, in the year 1477, a wealthy cloth merchant named Peter celebrated his daughter's wedding. The feast was a lavish affair designed to display the family's wealth and status. After the main courses of roasted meats and savory pies, a special dessert was served wafers. These were not the plain, simple wafers used for communion. These were crisp, thin, sweet biscuits, often flavored with cinnamon or orange water. And they were cooked in a very special tool. The cook brought out the wafer iron. It looked like a giant pair of tongs or pliers nearly 3 feet long with two flat circular plates at the end. The long handles were necessary to allow the cook to hold the iron in the roaring heat of the fireplace hearth without getting burned. But the most important part was the plates. They were not smooth. They were intricately carved by a skilled metalworker with Peter's family crest, a detailed rendering of a lion rampant. The cook's assistant had prepared a thin, sweet batter. The cook opened the iron, ladled a small amount of batter onto one of the carved plates, and quickly closed it. He then held the plates directly in the fire, counting carefully. He turned the iron over to cook the other side. The timing was critical. A few seconds too long, and the wafer would be burnt. A few seconds too short, and it would be a soggy mess. After about a minute, he pulled the iron from the fire and opened it. A perfectly crisp, golden brown wafer emerged, embossed with the image of the family's lion. This was not just dessert, this was edible propaganda. The wafer iron was an expensive custom-made object. Using it transformed a simple food into a symbol of the family's identity and power. In a time when most people were illiterate, a visual symbol like a coat of arms was instantly recognizable. Serving these wafers was a way of saying, "You are eating at my table, under my protection, and acknowledging my status." Other irons were carved with religious scenes, geometric patterns, or even short proverbs. They were a form of edible art, made possible by a specialized tool that combined cooking with printing. My Sunday morning breakfast often involves waffles. I have an electric waffle iron. It's a square stainless steel appliance that lives on my counter. It is not 3 feet long. I do not need to hold it in a fireplace. I plug it into the wall. I turn a dial to select how brown I want my waffles on a scale of 1 to 5. And a light tells me when it's hot. I open the lid. The two cooking plates are not carved with my family's coat of arms. They are cast in a simple, non-stick grid pattern of small squares. This is the classic Belgian waffle pattern. Its purpose is purely functional. The grid increases the surface area for a crispier waffle, and the little pockets are perfect for holding syrup and melted butter. I ladle in some batter. I mix from a box. I close the lid. The machine takes over. An internal thermostat monitors the temperature, cycling the heating elements on and off to maintain a perfect, even heat. After about 3 minutes, the waffle iron beeps. I open the lid, and there it is, a perfectly uniform, golden brown waffle. Every waffle I make with it will look exactly the same. My waffle iron is Peter's wafer iron. The fundamental technology is unchanged, a two-sided hinged cooking utensil for cooking a thin batter into a crisp patterned cake. The modern name waffle comes from the Dutch word waffle, which shares a root with the English word wev, referring to the woven, honeycomb-like pattern of the iron. The evolution is one of democratization and function over form. Peter's iron was a handcrafted, expensive, and deeply personal object. Its primary function beyond cooking was social display. My waffle iron is a mass-produced, inexpensive, and completely impersonal appliance. Its only function is to cook waffles efficiently and consistently. The intricate, meaningful patterns have been replaced by a generic, functional grid. What we gained is accessibility. Anyone can own a waffle iron and make perfect waffles at home. It is no longer a food reserved for the wealthy on special occasions. And it's a common breakfast item. What we lost is the artistry and the meaning. The act of imprinting a personal symbol onto food has vanished. My waffle doesn't say anything about me or my family. It is a generic, perfectly formed, delicious product of a machine. It's a better tool for making breakfast, but a lesser tool for making a statement. Number 4, your stand mixer is a butter-making machine. On a farm in Pennsylvania in 1790, a young woman named Sarah began one of the week's most physically demanding chores, churning butter. And the family had a cow, and the fresh cream had been skimmed from the milk over several days and allowed to ripen slightly in a cool place. Now it was time for the transformation. Her tool was a dash churn. It was a tall, cylindrical wooden tub, narrower at the top than the bottom, held together with iron hoops like a barrel. A wooden lid with a hole in the center sat on top. Through the hole went the dasher, a long wooden pole with a cross-shaped or circular plunger at the bottom. And Sarah poured about 2 gallons of thick, cool cream into the churn. She put the lid on, took hold of the dasher handle, and began to work. It was a simple but relentless motion. Up and down, up and down, plunge, lift, plunge, lift. The sound was a steady, rhythmic sloshing. For the first 10 or 15 minutes, nothing seemed to happen. She was just agitating cream. Her arms began to ache. Her back began to complain. This was a test of endurance. Then, slowly, a change began. The sound of the sloshing changed. The resistance on the dasher changed. The cream was thickening, turning into a whipped cream consistency. She had to keep going, pushing past this stage. After another 20 minutes of constant churning, the magic happened. Suddenly, the resistance gave way. The dasher moved more freely. The sound changed to a lighter, more splashy noise. She had broken the butter. She lifted the lid and looked inside. The cream had separated into two distinct products, clumped together on the dasher and floating in a thin, watery liquid were solid grains of golden butterfat. The liquid was the buttermilk. She had, through sheer mechanical agitation, forced the fat globules in the cream to clump together and separate from the liquid. The entire process took her about 40 minutes of nonstop, repetitive physical labor, and the work wasn't even done. She still had to gather the butter, wash it in cold water to remove the last of the buttermilk, and press it into a mold. Last night, I made butter. I bought a quart of heavy cream from the grocery store. I poured it into the stainless steel bowl of my KitchenAid stand mixer. It's a heavy, powerful appliance with a 325-watt motor and planetary gear system. I attached the flat beater, which is sometimes called a paddle. I locked the bowl into place, tilted the motor head down, and turned the mixer on to a medium-high speed. The machine whirred to life. The paddle began to spin, but it also orbited around the bowl, ensuring that all of the cream was agitated constantly and evenly. I walked away. For the first few minutes, the cream turned into whipped cream, forming soft, then stiff peaks. A few minutes after that, the whipped cream started to look grainy and yellow. Then, suddenly, at about the 10-minute mark, the transformation happened. The sound changed from a thick whir to a sloshing splash. I looked in the bowl. Lumps of yellow butter were being slapped against the side of the bowl, and a pool of buttermilk had appeared at the bottom. The mixer had done the exact same thing as Sarah's churn. Its constant, powerful agitation had forced the fat globules to coalesce. The entire process took 10 minutes, during which I was not involved at all. I just had to listen for the sound to change. The machine did all the work. My stand mixer, when fitted with a paddle, is Sarah's butter churn. It is a machine designed for agitation. While we mostly use it for mixing cake batter or kneading dough, its ability to make butter reveals its direct lineage to one of the most ancient and laborious of kitchen tasks. The gain is almost absurd. What was once a 40-minute muscle-aching chore is now a 10-minute, hands-off, automated process. And it turns butter making from a significant domestic task into a fun kitchen experiment. The power of the electric motor has completely replaced the power of the human body. But something fundamental about the product is lost to our understanding. Sarah understood the creation of butter in an intimate, physical way. She felt the cream thicken. She felt the moment the butter broke. She was the engine of the process. For me, the mixer is the engine. The process happens inside a metal bowl driven by a machine. I am just a spectator. The butter appears as if by magic, a magic powered by electricity, not effort. Number 3, your refrigerator is a man-made glacier. On a grand country estate in upstate New York, in the bitter cold of January 1880, a massive and difficult harvest was underway. But the crop was not corn or wheat. It was ice. The estate's owner, a wealthy industrialist, had a large man-made lake that had frozen to a depth of over a foot. Now, a team of 24 men hired for the purpose were on the lake with saws, axes, and horses. Their job was to cut the ice into large uniform blocks, typically weighing around 100 pounds each. It was dangerous, freezing work. Men used long, two-handled saws to cut deep grooves in the ice, then used massive chisels to split the blocks free. Horses wearing special spiked shoes for traction were used to drag sleds loaded with the glistening blocks from the lake's surface. But cutting the ice was only the first step. The real technology was where it was stored, the ice house. The estate's ice house was a large, windowless stone building partially buried into a north-facing hillside. It had thick double walls with the gap between them packed with sawdust for insulation. To prepare for the harvest, the floor was covered with a thick layer of sawdust. The ice blocks were brought from the lake and carefully stacked inside the house layer by layer. Between each layer of ice, another thick layer of sawdust was spread. When the house was full, holding perhaps 50 tons of ice, the heavy insulated doors were sealed. This was the 19th century method of refrigeration. It did not create cold, it preserved it. It was a massive, labor-intensive effort to capture the cold of winter and store it for use in the summer. Throughout the year, servants would go to the ice house, dig out a block of ice, and carry it to the kitchen's ice box, a smaller insulated wooden cabinet. The melting ice in the box would keep food cool, allowing the wealthy family to enjoy chilled drinks, ice cream, and preserved meats and dairy products long after the natural ice had melted. The entire system was dependent on a cold winter, a huge amount of manual labor, and very clever insulation. In my kitchen, there is a large stainless steel box. It makes a low, almost imperceptible hum. This is my refrigerator. A light came on, illuminating a space filled with milk, cheese, vegetables, and leftovers. The air inside was a consistent, controlled 37 degrees Fahrenheit. I have never harvested ice. I have never filled my refrigerator with anything other than food. The cold is just doesn't there. Always. The technology inside that box is a miracle of physics, a system that doesn't just preserve cold, but actively creates it. It's a vapor compression refrigeration system. A special chemical, a refrigerant, is pumped through a closed loop of coils. In one part of the loop outside the fridge, a compressor squeezes the refrigerant gas, making it hot. This hot gas runs through coils on the back of the fridge, releasing its heat into my kitchen. As it cools, it turns into a liquid. This high-pressure liquid is then pumped through a tiny nozzle into another set of coils inside the freezer compartment. As the liquid passes through the nozzle, the pressure drops dramatically, causing it to evaporate back into a gas. This evaporation, like sweat evaporating from your skin, is a phase change that absorbs a huge amount of heat. It makes the coils inside the fridge intensely cold. A small fan blows air over these cold coils, circulating the chilled air throughout the refrigerator and freezer, pulling heat out of my food. The refrigerant gas is then sucked back into the compressor to start the cycle all over again. My refrigerator is the estate's ice house. Both serve the exact same purpose to provide a cold, enclosed space for food preservation, but the methods are polar opposites. The ice house was a passive system. It was a giant thermos fighting a losing battle against the heat of summer. It was powered by winter and human sweat. My refrigerator is an active system. It is a heat pump, constantly working to move heat from inside the box to outside the box. It is powered by the electrical grid. The gain is one of the most profound in human history. The battle for food preservation, once a seasonal, labor-intensive struggle, has been won by a quiet, efficient machine, and has completely changed what we eat, how we shop, and how we design our kitchens. We are no longer dependent on the season or on a harvest of ice. But we have lost any connection to what cold is. For the owner of the 1880 estate, cold was a resource. It was a commodity that was harvested, stored, and used with care. For us, cold is a utility. It is something that comes out of a box, on demand, powered by an invisible force. We have no idea of the work it does, or the energy it takes to defy the second law of thermodynamics 24 hours a day in the corner of our kitchen. Number 2, your food mill is a horsehair sieve. In the kitchens of the Cluny Abbey in France around 1250, Brother Antoine was preparing a meal for the abbot, who was old and had few teeth. The meal needed to be soft, smooth, and easily digestible. On the menu was a puree of cooked turnips. Brother Antoine had already boiled the turnips until they were soft, but now came the difficult part, turning the lumpy fibrous mash into a silky puree. His tool for this was a sieve, or a tamis. It was not a metal mesh sieve like we know today. It was a large, circular wooden frame, about 2 feet in diameter. Stretched across this frame, like a drumhead, was a coarse fabric woven from horsehair. Horsehair was strong, durable, and wouldn't impart a flavor to the food. 2 kitchen boys placed the tamis over a large earthenware bowl. Brother Antoine ladled the hot, cooked turnips onto the horsehair mesh. He then took a wooden pestle shaped like a small, flat-bottomed mushroom. He began to work. He pushed the turnips against the mesh, forcing the soft pulp through the tiny openings in the weave. It was a slow, messy, and tiring process. He had to press and scrape, working in a circular motion. The tough fibers and any stringy bits of the turnip were left behind on top of the sieve. What collected in the bowl below was a relatively smooth puree. To get an even finer texture, the process would have to be repeated, perhaps with a finer weave linen cloth. This was the only mechanical method of pureeing food. It relied on pressure and a simple filter. It was labor-intensive, but it was the peak of culinary refinement for the time, a way to transform coarse peasant food into something elegant and suitable for a man of high station. Last week, I was making tomato sauce from scratch. I had a huge pot of tomatoes from my garden, which I had cooked down with onions and garlic. And I wanted a smooth, seedless sauce, but I didn't want to go through the tedious process of peeling and seeding all the tomatoes beforehand. So I got out my food mill. A food mill is a clever, hand-powered mechanical device invented in the early 20th century. It consists of a bowl-shaped body with a perforated plate at the bottom. A crank on top turns a bent metal blade that sweeps across the surface of the plate. I ladled my hot tomato mixture into the hopper of the food mill, which I had placed over a large bowl. I began to turn the crank. As the blade rotated, it did two things at once. It crushed the cooked tomatoes, and it forced the soft pulp and juice down through the small holes in the bottom plate. The tough skins and the small, hard seeds could not pass through the holes. They were scraped along by the blade and remained behind in the mill. The process was rhythmic and strangely satisfying. With each turn of the handle, a stream of beautiful, smooth tomato puree poured into the bowl below. The noise was a gentle, mechanical grinding. After about 5 minutes of easy cranking, the entire pot of tomatoes had been processed. All that was left in the mill was a small, dryish puck of skins and seeds, which I tossed into the compost. The bowl was full of a perfect velvety tomato sauce. My food mill is Brother Antoine's horsehair Tommy's. Both are tools designed to separate the soft pulp of a cooked food from its unwanted skins, seeds, and fibers. Both use the same basic principle, forcing food through a perforated surface, but the food mill represents a huge mechanical improvement. The Tommy's was a static tool. All the force had to be applied directly by the user, pushing down with a pestle. The food mill is a dynamic tool. It uses the mechanical advantage of a crank and a rotating blade to perform the crushing and forcing actions simultaneously and much more efficiently. The simple addition of the crank and the angled blade transforms the process from a messy, tiring scrape into a clean, easy, continuous rotation. What we gained is efficiency and elegance. The food mill is a far superior tool for the job. It's faster, cleaner, and requires much less effort. It allows a home cook to achieve a level of refinement that was once only possible through the hard labor of a kitchen staff. What was lost? Perhaps only the directness of the action. With the Tommy's, the cook is in direct contact with the food, feeling its texture change under the pestle. With the food mill, the work is mediated by a simple machine, a crank, and a blade. It's a small change, but it marks the shift from a tool that is an extension of the hand to a machine that replaces the work of the hand. Number 1. Your tofu press is a medieval cheese press. In a small dairy high in the Swiss Alps, in the year 1520, a cheesemaker named Ulrich was at a critical stage of his craft. For hours, he had been carefully heating milk, adding rennet, and cutting the resulting curd into small rice-sized grains. Now the curds and whey were separated. The future of his cheese, which would feed his family and be sold at market, depended on the next step, pressing. He and his son scooped the warm, wet curds out of the massive copper vat and packed them into a large, round wooden mold lined with cheesecloth. The mold was full of a loose, spongy mass. To turn this into a hard, long-lasting wheel of cheese, almost all of the remaining whey had to be expelled. This required immense, sustained pressure. They moved the filled mold to the cheese press. This was a huge, formidable piece of equipment built from massive timbers. It was a screw press, a huge wooden screw, as thick as a man's thigh, passed through a heavy crossbeam. At the bottom of the screw was a flat wooden plate called a follower. They positioned the mold under the follower. Ulrich took a long wooden lever, inserted into holes in the head of the screw, and began to turn. With each turn, the screw descended and the follower pressed down on the curds. At first it was easy. Milky, greenish whey began to pour out from the sides and bottom of the mold. As more whey was expelled, the curds compacted and the resistance increased. Soon, Ulrich and his son were both putting their full body weight into turning the lever. The timbers of the press creaked and groaned under the strain. The pressure was enormous, hundreds, perhaps thousands of pounds per square inch. They would leave the cheese in the press for a full day, tightening the screw every few hours as more whey was released. This slow, powerful pressing was what gave the cheese its firm texture and its ability to be aged for months or even years. The press was a machine for preservation, a tool that used mechanical force to transform a perishable food into a durable one. Yesterday, I made pan-fried tofu. I bought a block of extra firm tofu from the store. Tofu, much like fresh cheese curd, is packed in water. To get it to fry up crispy instead of steaming into a soggy mess, you have to get that water out. I needed to press it. I used my tofu press. It is a small, simple device made of plastic and stainless steel. It consists of 2 flat plastic plates with 2 long steel screws, one at each end that go through the plates. Large, easy to grip plastic knobs are on the top of each screw. I placed the block of tofu between the 2 plates. I began to turn the knobs. As I turned them, the top plate descended, squeezing the block of tofu. The effect was immediate. The water, which had been invisible inside the tofu, began to beat up on its surface and run down the sides. I gave the knobs another few turns, increasing the pressure. More water came out. I placed the press on a plate to catch the runoff and put it in the fridge. Over the next hour, I went back twice and gave the knobs another full turn, tightening the press as the tofu compacted. After an hour, the block of tofu was noticeably thinner, firmer, and drier. I had probably removed a half cup of water. My tofu press is Ulrich's cheese press. The technology is identical in principle. It is a screw press, a machine that converts the rotational force of turning a screw into a powerful linear force for pressing. It performs the exact same function to remove excess liquid from a block of curd in his case. Milk curd in my case, soy curd to improve its texture and prepare it for further cooking or preservation. The evolution here is one of scale and material. Ulrich's press was a massive permanent installation built of wood and designed to exert tons of pressure. It was an industrial tool for a commercial producer. My press is a small, portable countertop gadget made of plastic and steel designed to exert a few dozen pounds of pressure. It is a domestic tool for a home cook. What we gained is personal convenience. The ability to properly press tofu at home, easily and cleanly, is a small but significant improvement for anyone who cooks it regularly. The power of the giant screw press has been scaled down to a handheld device. What was lost is the sense of immense power. Ulrich's press was a testament to the forces required to create a durable, valuable food product. Its creaking timbers spoke of the huge effort involved. My little plastic press is quiet, efficient, and unremarkable. It does the same job, mechanically speaking, but the drama of the transformation has been completely domesticated.